Hello, welcome. I've called this talk Modern Web Application Bugs. It turns out that a lot of the stuff that we find to be modern is actually quite old, so we'll get back to that. But some of the stuff is modern in the sense that it's retro, it's come back. I'm either really stupid or quite brave because I'm going to do a lot of live demos, or at least some live demos, and those things can fail. And I don't have any video backup because it's demo or die. So my apologies if some of them don't work. I'm Erlend. I work at a company called Blank in Oslo in Norway. I spend most of the days as a developer, but I also do security testing, and I've also started doing bug bounty hunting. And this is kind of the place where I started to run into all these kinds of newer types of bugs that we can find. I also build open source security tools, and I'm head of the OS Norway chapter in Oslo, and you have my Twitter handle there as well. So we had a new revision of the OS Top 10 come out last year. And in this, we had a couple of new entries. We have A4, which is XML external entities, and A8, which was insecure deserialization. And for many of us who's been following the industry for some time, we were kind of waiting for this to come, because these are things that people have been exploiting a lot lately. If we go into the bug bounty space and read the reports from the companies, this is from BugCrowd, we see that it's kind of the old things all over again. It's like cross-site scripting is actually two places. It's down at the bottom as reflected and at the top as stored. And we have things like the classic stuff, really. If we go to HackerOne, which is another bug bounty platform, the font is a little bit small, but it says cross-site scripting at the top, and there's some SQL injection, and there's some stuff in here. If we're going to look at the newer stuff, we might have to move outside of these classic things. But the first thing I'm going to talk about is actually one of the things that is on the OS Top 10, the new version. And it has to do with XML, because XML is fun. So here's my first live demo. I have, at the top here, I have a URI, and I have some XML that I want to send to the server. And I can click this send button, and it will send the XML to the server and print the response in the lower window. So XXE, this is actually a bug that's been around since, I think, 2002. But it's come back a lot lately because people write new types of XML parsers, and they are vulnerable to this all over again. So the idea here is we can declare a doc type at the top here. And this doc type, we can define a system entity. And a system entity basically means go read this stuff from the system and then put this in the content entity. And then when we're using this entity down here, we're actually going to get the output from that file, which is handy. And we could also do things like replace this with a dot, which would mean list the files in the current folder. Oh, there's something called passwords.txt. That sounds useful. Let's look at that. Summer 2018. That's a good password. I'm sure no one else has that. But we can do more, because we could use something called XSLT, like we could transform an XML into an HTML. So in this case, we can send in, instead of sending in an XML, we're sending in a way to transform our current XML into an HTML. So it would become like a table with some stuff in it, really boring stuff. But of course, XSLT can have stuff in it as well. So we can start querying system properties like this. So instead of showing the XML that was boring, we're now grabbing stuff out of the system. So we can see which version of XSLT, which provider, etc. Down here. But again, not that super useful. What if we could read files, just like with the XXE stuff? Well, we can. There's a function called document in XSLT, which can bring in another XML document into the rendering. So in this case, I'm grabbing the POM XML. And for those of you who are not Java developers, POM is like package config or package JSON. It declares which kind of dependencies this system has. So that could be useful. But we can do more. We can have XXE in the XSLT instead of in the XML, because XSLT is also an XML. And that works just as fine as the other one. And also we saw that we had XSLT version 2. It has a new nice function called unparsed text, which means we can bring in files that aren't valid XML as well. Like this, stealing the file once again. Or we can actually start querying around the network. Instead of providing a file name, we could provide a URI. And in this case, we find that there's an Elasticsearch server on this network. And this might be something we couldn't access from the outside because it wasn't accessible directly on its IP. It was kind of behind the current server that we were looking at. So this is kind of scary. Luckily for .NET developers, Microsoft patched all their parsers back in .NET 4.5.2, I think it was. So you'd actually have to enable this for it to be vulnerable. But it's really important that you know this. Sometimes we don't get the result back immediately, so we can do something called blind XXE. And in this case, we're going to, where we can actually bring in, we can bring in an external DTD from our own hacker server. And this looks like this. And what we're going to do here is we're going to steal the contents of the file, put it in the data3 entity here, and then we're going to put that at the end of the URL down here, and we're going to, when this is parsed, it's actually going to grab the contents of this file and send it off as a part of trying to reach this URI. So again, we could steal stuff without even getting the response back immediately, as we saw in the previous examples. This is a report on HackerOne where someone found an XXE. These are really useful. You should go read this stuff because you can learn a lot from reading these things. There's one interesting thing with this one, and it's if we look at the severity here, they say it's medium. But if you look at the payout that was given to this Josh Brody, it was $10,000 from Twitter for finding this. So maybe the medium and the bounty is kind of out of tune. I don't know. So that was XXE. The next one is also on the OWASP Top 10. And it's called insecure deserialization. And this is something that's been researched a lot the last years. Talks on Black Hat and building of frameworks for doing this and all kinds of stuff. So what is this thing? Well, serialization is something we use for a lot of things. Like we use it for REST APIs. We use it for web services. We use it for all kinds of things where we have to transfer some internal object on the server into some format that we can ship across the wire or send down to a database. So it doesn't have to be a REST or web service API. It could also be things like a shared cache. It could be a file system. It could be all kinds of places where we're sending things back and forth. So and if this goes wrong, we could deserialize something into a dangerous object. And this could allow us to do things like denial of service. We could manipulate the state on the server. We could compromise the server. Or we could even get remote code execution. So I'm going to give you a very simple example first. So at the top here, we have the person object, which is a completely benign object. It doesn't do anything special. It has a constructor. It takes a name. And it assigns that to a property. Nothing special about it. And then at the lower part of the screen, we have a gadget, which is what we call these dangerous elements that we can use in deserialization attacks. And in this case, it's a util class. It's not meant to be a part of the API. But if we invoke the constructor of this with a string that points to a file, it would actually start this file as a process. And normally, this is hard to achieve because we can't really target that special file. But for some reason, it's possible in some of these frameworks to enable specifying the type. So if we look down here, we see in this JSON, you can specify the type that this is supposed to be deserialized to. And same thing for the XML down here. And if we could do this, we could actually just send in either this JSON or this XML, and it would actually start a new process. But this is a bit oversimplified, because usually we don't have things like this lying around. So we have to change stuff. And this is one example for a .NET deserialization gadget, which is using something called object data provider in the presentation framework. And then it's doing some stuff to bring in a process, and then an array list of arguments, which in this case is the calculator. And then it invokes the method called start on this. But let's do demos on this as well. So I have here, this is a Java deserialization attack, where it's the same API that we looked at earlier, but in this case, this time we're going to create a proxy for the contact object. So this is, I'm not going to go into detail on how this works. But if we try to do something like this, it's going to create a process builder, and it's going to run ping with some stuff here. But of course, we can't see what's going on, and it appears that it failed down here. So, But let's do something more interesting. We're going to create a small little listener on our hacker server. So we're going to listen on a port, and then we're going to try here to create a remote shell back to this server that we're listening on here. Boom. Now I'm in on this server, and I'm logged in as root. Quite dangerous, I would say. So these things are super scary. This is an example from Starbucks in India, once again from HackerOne. Someone found a code injection here in something called JBossMQ. And these things happen a lot. And really, go read these reports. They're great. The next thing we're going to look at is something called server-side request forgery. You might have heard of client-side request forgery, CSRF, which used to be on the OWASP top 10, but was recently removed. And server-side requests are kind of similar, except they happen on the server. So we can trick the server into doing something it shouldn't do. So we could have a setup like this. We have a browser which talks to a reverse proxy or some other type of server-side application, which again talks to another server. So this could be like a microservice or something like this. And sometimes we're able to influence how this second call is made. So I'll give you an example here. We have a request coming in from the browser, and it goes to example.org/images/200x200/product.jpg. And in the server application, we're going to replace the first part of the URI before we actually make the lookup to the backend system. So we're going to take the original URI, just drop something of it, and then replace it with images.example.org and go grab the file and then stream it back to the end user. So we strike out the first part, and then this is the end URI that we actually look up. But there's quite a few problems with this. First of all, what happens if we did this, like images.evil.com? Well, it's going to remove the first part, and it's going to look up images.example.org.evil.com, which is our server. So that's useful. Maybe they use some kind of authentication tokens that we can steal. Also, we could do something like this. And in this case, it would be images.example.org and then dummy. So this would be a basic authentication where images.example.org is the username and dummy is the password. And then we try to fetch stuff from an internal server. It could also be something like this. Maybe we have some functionality in this application where we're supposed to be able to import some data from an external source. And we could start poking around the internal network instead and grab some stuff from a MongoDB or something like this. Or we could even do something similar to the XSE stuff. We could start grabbing files, which could be useful. But one of the things that this is very often useful for is grabbing stuff from cloud services. So on EC2 and other types of cloud providers, they have a special IP. It's 169.254.169.254. This is the metadata host. And it can provide things like security credentials, so basically keys to log into the server. We could also use this, of course, to grab stuff out of databases or other services. But recently, it's been used a lot for these cloud services. So what we're thinking now is, OK, so this IP is dangerous. Let's block it. Turns out that that can be quite hard. So a guy called Nicolas Grégoire, who's a French guy doing a lot of SSRF research, he found that a lot of IP address parsers, they are very permissive. So we have our regular IP, and then we have our regular IP with overflow. So it's just going to truncate it. It's going to do mod 256. And so these are basically the same IPs. This is an numeric IP. This is a numeric IP with overflow. This is a hex IP. This is a hex IP without dots. This is a hex IP without dots, but with overflow. This is an octal IP. This is an octal IP with overflow. OK, so this IP stuff is kind of hard. So we're not going to allow IPs. We're going to just allow host names instead. Okay, I could of course set up my DNS to point to the same IP or to localhost if I wanted to. There are actually services that do that already. So you could just do the ip.zip.io and it will resolve to 127.0.0.1. We could base36 encode that IP so it's not that visible. Or we could even do like a fake host name at the front there. So www.bank.no and this base36 thing and then zip.io, which again resolves to 127.0.0.1. Also, 0.0.0.0, that's usually like all the interfaces of our system. So we might be able to reach stuff there as well. And it turns out that 127 is also like, you don't have to do 0.0.1. That's what we normally do. But you could do 127 4 times, and that would work as well. And then IPv6 comes along, and we get all this other kinds of weird stuff that pops in. And this is, once again, an example from HackerOne. Someone found one of these. And if we look closely here, we can see all the way down here a very familiar IP, 169.254, 169.254, so the same IP. So as I said, this is one of the things that people have been using SSRF for. They can go grab these access keys, and then they can basically SSH into the server with these access keys. The next one we're going to look at is something called template injection. This is, it's kind of a part of the OS Top 10 because you could probably put it under A1 injection, but it's also quite new, and it's also related to the way that we use different types of frameworks. So a template could look something like this. So we have these curly braces. They tell us that in this place we're going to insert some data. And what a lot of these frameworks will actually do is something like this. So they'll pull out the strings, and then they'll do an eval of the stuff that's in between and to run it, basically. And that as long as we are the provider of that template, that's fine. I mean, we added the stuff in there, and we are the developers of this system, so that's fine. So if we had a template that looked something like this, and we had a title variable that contained hello, the end result would be h1, hello. The problem occurs when we try to combine templates. So we have one template, and we want to have like a module system, so we want to bring one template into another template. And we do it the wrong way. So in this case, we render the first template, and then we insert the rendered result into the second template. So if they both contain normal strings, there's no problem. It's hello and it's world, and things render properly. But if the first rendering contains a template, that template is going to run as part of the evaluation of the second template. So in this case, title is 2 by 2, and with the curly braces. And so it's going to be rendered into a new template, which we insert into an existing template, and then we double evaluate the first part, which is the dangerous thing. So no fun without a demo, right? So here I have an application, and if I click here, it just, and I specified my name up here, it just says, hello, Alan, and we have my name down here as well. So in this case, it renders the HTML on the top, and it shows the source of the HTML at the bottom. So we could do 2 times 3. And it says hello 6, because it double evaluates this. So we see that this comes back from the server as a 6. But of course, math, we could do that in calculator. So let's do something more fun. Let's try to figure out what's running here. So self, okay, some error thing going on. But it also reveals something here. This is a Twig template, and Twig had some bugs in it. So let's bring up our hacker server. And first, we're going to just test that we can run code. And in this case, we ran the ID command, which gave us which user this application is running as. But we could do something like this instead. So now, if you saw, I now have shell on this server. I'm logged in as www.data down here. So I've hacked into this server as well, just with a simple URL. Okay, sorry. I'm just going to do like this. There we go. But this was server side, right? We saw that 2 times 2 or 2 times 3 came back as 6, but we can have template injection client side as well. So in this case, we have one templating framework running on the server, and we also have Angular. So if we look down here, we see it came back as 2 times 3, but up here as rendered, it said 6. Because Angular went in and saw, okay, there's something going on here. There's an ng app, and there's a template, so I'm going to run this template. And this is something that can happen if you're mixing a server-side templating framework and a client-side templating framework. But of course, once again, math is no fun. So we could do like alert 1, right? No, because this is Angular, and the earlier versions of Angular, they had a sandbox, and that sandbox tells us that you are not allowed to execute functions like that. But then, of course, this Angular version also had a bypass of the sandbox, which was you create a string, and you get the constructor of the string, which is the string constructor. And then you get the constructor of the string constructor, which is the function constructor. And then you create a new function containing alert1, and then you invoke that function. And then we get the alert. So we have cross-site scripting. And the funny thing here is you can see that, and it runs 2 times as well, and you can see that it was encoded down here, but it worked anyway, because that's just the way it works. So we have to take care of these things. Like we're using templates and we're mixing things up, we have to take care of this. We get some new control characters in the mix when we're doing these double types of templating. So if we're going to stop template injection, we need to make sure we don't double evaluate these templates, and mixing server-side and client-side templating is also a really bad idea. And this was actually in the documentation for Angular for a long time. But at the end, they decided just to drop the entire sandbox because people find bypasses for these sandboxes all the time. Don't mix server-side and client-side templating. The next thing we're going to look at is insecure CORS. So CORS, or cross-origin resource sharing, is a way for our system to tell a website running on a different domain than ours that it's allowed to read data from us. That's basically it. So we can use this header called access control allow origin. But sometimes people have a hard time understanding what it does. So I got some help from Google Translate to translate from HTTP to English. So access control allow origin example.com and access control allow credential true. So if the user is logged in and visits example.com, please allow that site to access the user's data. Okay, that's probably what we want. But then we see developers doing this. Access control allow origin, access control allow credentials true. And translated, it means if the user is logged in, please allow any site on the entire internet to access the user's data, given that they can trick the user into visiting their site. Luckily for us, the browsers get really angry if we try to do this. They say, okay, this is an insecure policy, you shouldn't do that. But our friends, the funny developers, they sometimes figure out ways around these policies because maybe they misunderstand what these things do. And I was writing some code the other day, and one of the frameworks I used had the bug I'm now going to show you as a feature. So the mistake number 1 is the echo. So we grab the origin header that comes in from the client, and we just echo it back as access control allow origin. So now we have access control allow origin star. It's just not explicit anymore. So just going to echo whatever. So any site on the internet can now steal the data once again. We just circumvented the policy. Mistake number 2, insufficient validation. So, okay, we grab the origin header and we check, does it end with example.com? Okay, we're going to allow it, which means we also allow not example.com because that also ends with example.com. Next one, null. All right. What does this mean? Access control allow origin null. Access control allow credentials true. Let's ask Google Translate. So if the user is logged in, please allow any site the user visits to access the user's data as long as the site knows how to use an iframe with the sandbox attribute. Like this. Because if we create an iframe with a sandbox attribute and we use like this data thing here, we're going to get a null origin. And so what would actually be sent is origin null, as you can see at the bottom here. So that's also a completely unsafe configuration. So a guy called James Kettle, who works for Portswigger, and Portswigger is the creator of the very famous hacking tool or pen testing tool called Burp Suite. He did a lot of research into this, and this is one of the things that he found. So course misconfiguration on somato.com, and it would allow things like not somato.com. So the exact same thing that I just showed. So that's interesting. Next thing, subdomain takeover. For those of you who were at Kieran Jacobson's talk earlier today, the boring security talk as it was called, he actually mentioned this, but under the name DNS squatting. So a Swedish company called Detectify, they have one of the most famous bug bounty hunters around in Frans Hussein. And he wrote a long blog post about this a while back. And this, what this does, it exploits forgotten DNS aliases. So a lot of the cloud services that we can use, they have these things where you can specify your own name as a part of the URI that points to their servers. And that allows you to kind of specify a part of the name that's yours. And for other types of services, infrastructure as a service services, we also can sometimes specify our name, or we get some kind of an ID up front. And Detectify, they discovered that there are over 100 services that allow these kinds of things. And so, but let's do an example. So we are a company, and we create an application that's running on Heroku. I think actually Heroku is changing this now, but let's consider that it works as it used to right now. So we create an application at ndc.herokuapp.com. But we want this to have a proper, our proper domain name, not like Heroku app. We want it to be our domain name. So we want ndc.example.com to point to this. So we go into the DNS and we set a CNAME, like an alias. So we say that ndcexample.com, you're going to go and look up this somewhere else. So we do an NS lookup for this, and we ask the name server. We're going to get back, well, you have to go ask this other thing. So we can demonstrate this with arrows and boxes instead. So we're going to look up ndc.hackable.network, for instance, and we're going to ask DNS of hackable.network. Where can I find this? We're going to get back. Go see Heroku DNS for this. And so we go to Heroku DNS, we ask it, we want the IP of this thing, and we get an IP back. And now we can go and visit the actual site that we wanted to. So that works perfectly, and we're happy, and we've been using this application for a while. But then at some point, we don't need it. So we remove it. We go into the Heroku GUI, and we just delete it, and we say, we don't need it anymore. Then we forget about this DNS entry. And then our friend the hacker comes along and creates a Heroku app with the same name that we used to have. And the attacker now controls our subdomain. That's not nice. Phishing with a proper domain name, that's probably pretty effective. You could use this to also steal or inject domain-wide cookies. You could add all kinds of stuff that would make the company look bad, or you could even create HTTPS certificates for that domain or for that subdomain. So here we have an example of this. This is a guy called Matthias Karlsson, also a Swede, who found one of these at Shopify. And here's another funny example. This is the certificate transparency log. And what's interesting here is if you see the name of the certificate. Simon Gursky has hacked prod2.uber.com. He was able to grab one of their subdomain and get a certificate for it. And because the CAs are, they have to publish all the certificates that they create. So this stays in this log like this. And yeah, so they're probably not too happy about that. The last thing that we're going to talk about is something called web cache poisoning. Now, web cache poisoning is something that, again, it's James Kettle of Portswigger did some amazing research on this. What he was trying to do was to exploit unexploitable bugs. Sometimes there are bugs in web apps where we can trigger some stuff that's going to happen, but we can only trigger it for ourselves. One of those things is, for instance, self-XSS or self-cross-site scripting. So I can send in a request from my browser and I can get cross-site scripting, but I can't send it to anyone else because you would have to set like this weird header or something. And you can't trick another browser for another user to do that. You have to control their system. But what if we could do something with the cache? So the gist of this is we have a server where our application is running. We have the cache sitting up front. The first client comes in, asks for some content. Well, there's nothing in the cache for it. So the cache server will go to our server, it will grab the content, store it in the cache, and then return it. So now the next client comes along, asks for some content, and gets a hit because the content was already there. Yeah, the second client asks for the same content as the first user. So there was a hit. And so there's no need to go to the backend server anymore. We have a cache hit. Nice. Then the attacker comes along. The attacker does something malicious, and there's no hit on the cache in this case. So the request goes to the backend. The backend gets this malicious data from the attacker, does something stupid with it, and then this thing is stored in the cache and returned to the attacker. But now, when the next client comes along, there's a hit, and it's the attacker stuff. So our unfortunate client that comes along later is going to get the poison data. So the attacker is able to poison the cache, put some bad stuff in there, and that's not very nice. So let's see how this works. So what I'm showing you here is we have the headers that I'm going to send at the top here. So I'm going to send it to the URI you see at the top, and these are the headers I'm going to send. So send this on, and the important thing to look at here is this thing here. So it says, I'm going to load a script from web.hackable.network. Okay, nothing bad going on. But then the attacker comes along. And the attacker sets another header because the attackers figured out that this application, if it gets this header, it's going to use it the wrong way. And X-forwarded host is something we often use in reverse proxy to tell it that this was the original host that came in, and you should treat it as such. So the attacker can now do this, send in this, and in this case, we see that it says attacker.com here instead because this was used the wrong way. The URI is a bit different though. There is something at the end here. So our friend over here will still see web.hackable.network. So what we can do, we have to poison the exact same URL, or at least we have to figure out which parts of the parameters are a part of the cache key. In this case, if we try to poison it without anything, or I can actually show you this first. We can poison it with this, like this. It says attacker.com. If I now try to change it to, let's say, not attacker.com, and I try to send it, now I'm just hitting the cache. So it still says attacker.com. It doesn't change to not attacker. But if I change this URL parameter, because that's the part of the cache key, it's going to change down here. But I want to poison the root. So now I'm going to try this. And we now have not attacker on the root. So our friend, the friendly client, comes back, and it now says not attacker.com without this user sending this header. But this is boring. Now I want to hack you guys. So please bring out your phone or your laptop and try to go to this URI. There's nothing dangerous there, no worries. I promise. What do you see on this URI when you open it? So it's www.hackable.network. You see the NDC conference logo, right? So it should look something, oops, sorry, ruin it. So it should look something like this, right? That's what you see. So now I'm going to try to poison this page. And this might take a bit of time because there's a cache. this thing is pretty friendly for us down here. It says how long it keeps the cache. So it's a cache control public max age 60 seconds. That's helpful when we want to poison caches. So now my slide set is hammering this server trying to poison the cache. And hopefully at some point after about a minute, it's going to say success instead. And we'll see. Success. Now try refreshing the page in your phone. What do you see? Yeah, too bad I spoiled it already, but you should now see this person instead. So I just poisoned it. I didn't do anything on the server. I wasn't logged into the server or anything. I just poisoned the cache with this. So there are some tricky headers involved here. These are some of the headers that James Kettle found. X-host or X-forwarded host, they basically do the same thing. They tell it which probably was the host. But some systems also support things like X-original URL or X-rewrite URL, where you can actually trick the cache into caching things as a different URL. So you can send in on one URL and make it cached as another URL, which is kind of strange. And of course, very useful as an attacker. So what James Kettle did was he scanned like the entire internet and found a lot of these things, and a lot of the big services were vulnerable to this. But hopefully, most of them have now fixed this stuff. What can complicate this attack is we have to know which URL parameters are used in the cache keys. And this can be kind of difficult to do by hand because there can be a lot of URL parameters and we don't know which ones are important. Sometimes user agent is used, so you could poison the cache for a given type of a browser. So you could cache it. You could poison it only for Firefox or only for Chrome or only for IE. Maybe if it was like an old IE version, you could poison it for only that version, and then you could, instead of changing a picture, you could run an exploit, which could be useful. So you could target specific groups. James Kettle created a plugin for Burp Suite called Paraminer, which actually does this for you. It tries to figure out which headers and parameters are actually a part of the cache key. So that can be quite useful to test with. So how do we stop web cache poisoning? It can be a bit difficult. We should at least not allow these headers to come in from the outside, because if we go back to this drawing here, there's no reason why this X-forwarded host header should be allowed from the outside through the cache and into the server itself. It should be stopped here. There's no, if we're using this header, it's probably need to be used between the cache and the backend servers. We don't need the attacker sitting on the outside to be allowed to specify it. So we should probably block those or replace what's coming from the outside with something that we control. We could also add the headers to the cache key. So instead of someone being able to poison it for everyone, they can only poison it for someone with the same host header, which basically would mean the attacker is stuck back at the problem where it's unexploitable because you can't send this thing. We could also use the vary header to specify. Sometimes you can have the backend service specify which headers and things are supposed to be a part of the cache key. But other times you have to specify it in the cache itself. Of course, you should sanitize and encode all input. So what we could do in this case, instead of just replacing the host name, we could probably also do a cross-site scripting attack, because we could. Of course, this was a cross-site scripting attack to begin with, because what we did here was basically replace where it was loading this thing from. But we could try something like this as well, just to see what happens. Just to change this, because I loaded it now. Oh, I changed the wrong thing, sorry. This one. I'm just going to change this to 5. So now I kind of exited this thing. So if it was like just a string inside somewhere, I could now break out of that, and I could do cross-site scripting this way. So this is normally how this self-XSS stuff would work. And we could audit our pages with Burp Suite and this Paraminer extension. But of course, Burp Suite is a tool that it costs money. It's not a free tool. There is a free edition, but you can also purchase it. But it's quite cheap, and it's really, really good. So I highly recommend that you try it if you haven't. Here are some resources if you want to read more. I'm going to let this stay there for a short while. The top one is Disclosed H1. This is a Twitter account which publishes all the reports from HackerOne which are made public. So it's really nice to just follow that one. And whenever someone, one of the programs on HackerOne, they publish a report with some details in it, they're going to tweet it. You could also go to HackerOne to under Hacktivity, and you could find it there. The next two links are some tools called WISO Serial. These are deserialization tools. So you have WISO Serial and wisoserial.net, and these allow you to do these deserialization attacks on different systems. We have some things that I find useful, like the XSLT for practical attacks and the Serverside template injection, once again by James Kettle, which I used for creating the template injection thing. You have the blog post from Detectify, hostile subdomain takeover using Heroku, GitHub, and etc. Nicolas Gregoire has this paper, which actually slides, I think, from a presentation he did only on SSRF. You should actually look up the video because he has some really great examples in there of how he's used SSRF to hack things. Then there's Exploiting Course Misconfiguration for Bitcoins and Bounties by James Kettle that he did at the AppSec EU last year. And then there's a blog post and a paper and a presentation from James Kettle on practical web cache poisoning that you can find on the Portswigger blog. And that's it. The demo app, actually, that I used to run XXC and deserialization is on GitHub. So you can find it, you can run it as a Docker container, and in the README file, you can find all the things that I sent to it. So you can try it out yourself if you want to. Any questions? No questions. Clear as day. Or are you all scared and want to go home? All right, then I'm just going to stop. Thank you.